Okay, so welcome everyone to the fourth installment of binary exploitation course. Last time we were together, we were talking about stack exploitation, and we made quite some progress. And so today we'll be moving on to heap exploitation. We will omit this slide because everybody knows me already, so that's not so important. As suggested, last time we were talking about return to libc technique used on stack, so stack-based exploitation. Can somebody tell me what's the point in return to libc technique? I know that some time has passed between the last session of binary exploitation, but if somebody can just, if somebody has any idea what's even the general point. Are we overflowing something? Are we I know we have to leak something, we have to overflow something, we have to jump everywhere. Does anyone know what is the general idea?
Yeah, we have to write to a table which has, I think it's a GOT table.
Okay, so we have a GOT table.
This table has libc functions in it.
Great.
And we just change one of these pointers to system.
Okay, yes, great. So we'll be using global offset table to leak some pointers. Why does global offset table have libc pointers in it? Does anyone remember that? Or what? It's cache, yes. It's used in lazy binding. So this is when the program needs to resolve libc addresses on the fly, so it doesn't store them in the table at the beginning of the execution, but it resolves them as it's running in runtime. Okay, great. So we use the global offset table to leak a pointer, and then we calculate libc addresses, and then we do what? So it's a stack-based buffer overflow, right? Yes. The idea is to overflow some buffer, char buff 10, and to overflow, this is RBP, RSP. I'll just rewrite the registers again. So RSP is the stack pointer, RBP is a base or frame pointer. Then we have RDI and RSI arguments. Okay, so in the return to libc we talked about overflowing the return address on the stack, and first jumping into global offset table, where we used some function that writes to the standard out, so printf or puts, to leak its own address from the global offset table. Okay, but what then? What was the plan then? So now we've got the libc leak. Now we want to execute a shell. We want to get a shell as a proof of concept that we've successfully redirected code execution. Which function in libc can execute arbitrary programs on the file system? So basically binsh. System, great. So the plan is to, at 1, leak libc, we've done that, calculate the offset to system in libc, and then overflow the return address and build a ROP chain to call that libc with an argument of binsh. Where does the binsh come from? So we still need a pointer to binsh. So last time we had the whole exploit where we crafted some custom ROP chains just to write this sequence of characters bin sh somewhere in the memory and then use that. But that was a trick. I tricked you. We didn't have to do that. Why not? Where is libc? I mean, where is bin sh? So bin sh is already in the libc. So when we calculate the address of system, we can just as well calculate the address of bin sh. Okay, that's the general idea of the return to libc. We won't be talking about stack exploitation today. I just wanted to remind you guys of what we did last time. Share libraries. This is the libc. Basically, this whole demo, quick demo, just covered everything there. Are there any questions about any of these? They won't be so important today. There is no correlation between these techniques and what we'll be talking today. But if somebody has some questions from the previous time, you can ask them now. Okay, cool. So, what we'll be talking today. First, we'll do a recap of global offset table. I kind of started that already, but we'll do an actual recap. We will basically look at the slides we've already looked at previous weeks. And after that, we will be comparing stack and heap from the perspective of exploitation. So what is the difference between exploiting a stack and exploiting a heap? And then we will dive into how the heap is structured, the chunks, and how the heap is laid out. We will talk about free bins, we'll talk about how malloc works, and in the end we will show some common attack patterns, and we'll take a look at a very widely used and widely known vulnerability that is present in almost every binary exploitation zero-day exploit today. That's the use after free vulnerability. Here it says use after free Tcache poison. Sometimes this is very specific. So Tcache is specific for the x86 and the GNU libc malloc function. But use after free is a vulnerability that is present in every architecture. I mean, in every allocator structure. So it's not malloc specific in this case. What it means is we use some memory that's already been freed. Either we read from that memory or we write on that memory that's already been freed. Okay, first, the recap of the global offset table and the procedure linkage table. So the two tables that PLT is used to call a function. So we have PLT and a GOT. So every PLT entry points to a GOT entry, and at the beginning this one is populated with some addresses and this one is empty. So there's nothing here, null. And the idea is, no, I was wrong here, that's not true. It's an address that points to the DL resolve. The idea is that when using lazy binding, when we call the PLT function, it will resolve the function we're trying to call. So let's say we want to call printf.plt. It will resolve the function in question, so printf, and it will store the address in the global offset table. And why am I talking about this? Because of the lazy binding, because the global offset table is writable. We can easily redirect code by overwriting these entries. So here we overwrite this into bad function. And the next time we call printf, we will actually be calling our bad function. So these were the PLT and the global offset table. It was just a quick recap. We already talked a little bit about them here. Any other questions about these two tables? They should be pretty clear by now. Just some recall. Here, okay. Okay. Some technical issues. Okay, lazy binding. And here this is the, we also looked at that at the last time. So basically you have some images about how the whole process of rewriting global offset table works. So at the beginning, this is the first image, global offset table points back at the PLT and in the DL time resolve. But then when we first call a function, the global offset table starts pointing to the libc. And every subsequent call, there is no resolution, just address gets taken from the global offset table and we jump there. Okay, a quick recap about shared objects. So we will be talking a lot about libc, not a lot, but we will mention libc today, so it's good that you remember how the shared objects work. So the shared objects are like a big storage that is somewhere, and then we have a lot of processes that use the code. I'll just switch up this. That use the code in the .so, so progena, prog1, prog2, prog3, and they are basically reusing the same code. Let's say program Anna or process Anna calls printf. It will take the code from the shared object, shared library, which is somewhere in the RAM and somewhere in the memory. And then the program 2 decides to call scanf. It will take the code from the shared object in the memory and reuse it, and the P3 will do the same thing. So what I want you to know, what you want to keep in mind, is that all of them, just the resolutions are different. Okay, now I will wipe the board because we will dive into heap. Okay. As mentioned before, today we will be talking about heap exploitation, and here are just some headers as to what's the actual difference. So the environment starts to matter a lot. So when you're doing heap exploitation, everything is very fragile. You cannot just work with any libc, and every libc is very different in case of heap exploitation. Like when you talk about stack exploitation, yes, if you have a buffer of 100 characters, if you use libc 225 or libc 235, one is 10 years old and the other is 10 days old, it doesn't really matter. The stack will stay the same, mostly. But if you take a look at heap allocations in 225 or in 235, they will be drastically different. I think even the malloc.c file almost doubled from these two libcs alone. Your setup starts to matter a lot. Why? Because you can't just have one system to exploit on it. You can't have a natively running Linux, and let's say I'm running Ubuntu 18 and I want to do heap exploitation on that. Not gonna work out because of the libcs. So Ubuntu is natively running some libc version, and if I want to exploit an application that uses another libc version, then it won't work, because locally on my machine, the exploit will behave differently, a lot differently than on the server or wherever that a particular piece of code is running. And you will find yourself reading the libc source a lot. So basically this is the point where you start to actually dive into the every detail of how malloc is structured, how the heap allocations work, how the free bins work, how the lists work. So, and you have to know the code. You have to know that whenever you call malloc, A, B, C, D, and F will happen. But sometimes, even if you know a lot, you can't know everything, and in that scenario, if you find a bug in software and you don't know why exactly it appears, but there's an error message, let's say, thankfully there's an error message that says, I don't know, malloc failed because of A, B, C, or D, then you can search for that error message inside the glibc code, and you will probably find what the problem is. But you have to be used to looking at ugly C code, basically. And the heap is very fragile. So as I mentioned before, you can have a stack layout that's basically always the same on every server, on every environment. 100 bytes is 100 bytes, give or take. But if you have a heap, the environment variables matter, the user matter, the permissions matter, everything matters, almost the architecture matters. Like, it can be different on every setup, so heap is very fragile, and heap exploits are sometimes involve things like heap spraying, where the attackers don't really know if the exploit will work or not, so they spray the entire thing, the entire heap or the entire allocated memory with some gadgets or some malicious code, and they just hope it's gonna hit, because heap is so fragile that it doesn't behave the same every time. Okay, so this is how generally, very roughly, how heap is structured in ptmalloc2, so libc GNU malloc. Probably most of you here know what malloc is. You've used malloc before. Yes? In C, programming in C, you need malloc or calloc or realloc, whatever. So this is how the heap generally looks like. You have a heap header. It's only present from libc 2.26 and onwards, because then the tcache was introduced. We will take a look at tcache later. And then you have chunks. Chunk is basically a set or space of memory that malloc or calloc will return. When you call malloc and you give it a size, it will return a pointer to a chunk, and the chunk will be the size that you specified. That's it. These are the chunks. And memory on heap can either be allocated or free. So you can have chunks on heap that are being currently used, so they are allocated, or that are not being currently used, and so they are free. See, in this scenario, chunk 2 has been freed, and chunks 1 and 3 are being used, so they are allocated. Then we have a special chunk that's called the top chunk, or the wilderness, and it's there to speed up the allocation process, and we will take a look at the top chunk closer in the next slide, so I won't talk about it much now. But what I want to talk about is how the actual chunk looks like. So okay. Where is it? AMP, yes. I have AMP. Okay, this is how a general chunk looks like in memory. So this is 16 bytes. This is 16 bytes. So this is 8 bytes and this is 8 bytes. It's an address. So here is pref size, and here is size. Size. And down here is the user data. And this is the pointer that malloc will return to you. When you call malloc and say malloc size equals 20 bytes, malloc will return a pointer that points here in the user data. And here will be 20 bytes for you to use. What is in the header? So the header is these two values. We have size, so basically how big the chunk is. And we have the previous size, the pref size field, which is not used when the chunk is allocated. This field is not being used when the chunk is allocated, but when it's freed. What does it say? It basically concerns the previous chunk. So it says here is written a number that represents the size of the previous chunk. So if we have a heap setup like this, and this is the header, and then we have chunk 1, chunk 2, chunk 3. When we free this chunk, this prev size will be set to size of C2. This is how the prev size field works, and it's used for coalescing or for merging chunks together. So in the scenario that this one gets freed as well, it will not stay in its current form on the heap, but it will merge together with the chunk above him. That's why the prev size field is used. We'll take a look at coalescing or this merging in the later slides, but now I want to talk about the P, the AM and P bits. So the size value is always 16-bit aligned. For instance, the smallest chunk possible that you can allocate is hex 21 in size. Even if you say malloc 1, malloc will always return you at least this size chunk. And the next size that is possible to obtain is this one. So you cannot malloc a chunk of a size something like that. That's not possible. Why? Because of these bits and because the sizes have to be 16-bit aligned. That's the reason for it. And these 3 bits, and also why is here 1? Why is it not 20 and 30? It's because of these 3 bits. So these 3 bits are the least significant bits of the size value, and they represent the A bit is set if the chunk does not come from the main arena. Main arena, the arenas are used for multi-threaded applications. So when you have a program that spawns multiple threads and all of them are using the heap, are calling to malloc, they will have different chunks and different heaps, let's say, that all that don't belong to the same arena. They have every arena for themselves. So let's say arena 1 is the first thread, arena 2 the second thread, and so on. So this is what the A bit says. The M bit will tell you if the chunk has been M mapped. Malloc does not M map anything. Malloc does not create new memory. Calculation. Or you want to reserve your own space. Look something like this. Because the first 2 bits are set. So it's 3. 2 plus 1. And also, yeah, the P bit is that the previous chunk is also allocated. So in this scenario, before we freed C2 and C3, both of them had P bit set to 1. Because the chunk above is not free, is in use. And that's why always when you allocate, you get the size of something 1, because this bit is set to 1. If you would M map something, you will get the size of this, because both of the bits are set. And if you somehow manage to do all 3 bits, then you would get the size 7 or something. So yeah, basically I lied before. This size is possible. But the size, I don't know. I mean, they are possible, but you won't see them in malloc. That's what I meant. They are possible to have, but I've been looking at the heaps and stuff for a while, and I've never seen a chunk of a size being allocated. That never happens. It is theoretically possible. Okay, so this is how a malloc chunk looks like. So this is the chunk that was allocated in the memory and is ready to use. But as soon as we are done with the chunk, we have to free it. We have to call free and this same pointer. And when we free chunk, so now this will turn into free, some pointers are put over the user data section. So we have the FD and the BK pointer. These are the forward and the backward pointer. And what they are used for is for addresses. So on the FD pointer goes the address of the next chunk in the free list. What are free lists? List is basically, they are linked lists, sometimes singly, sometimes doubly linked lists. But if we free a chunk, it will end up at the beginning of the list, and in its forward pointer will be put an address to the next chunk. And this one has the forward pointer to this one, and so on. It's a linked list. That's it, nothing special. And also, if a chunk is free, its size will change from 3.1 to 3.0 because the chunk beneath that. So when we free, let's say we free C2, then the C3 will change P to 0 because the chunk above him is not in use anymore because it's been freed. Okay, and the main difference between allocated memory and not allocated memory is that you should not access memory that's not been allocated. So if we free a chunk, you should not be able to read from it or write to it. That's called a vulnerability. That's called the use after free. So that's the big thing. Okay, so I mentioned before the bins. We know a lot of free bins. So there's tcache, fastbin, and unsorted bin. These are the ones that I'll talk about today. But we also know the small and the large bin. I won't talk about them today because they are not relevant for the exploitation part that much. They have some vulnerabilities and some useful techniques, but mostly are not being used in the exploitation world. Okay, but the first one that is very interesting and was a disaster when it was firstly implemented in the glibc was the tcache. So while I wipe the board, are there any questions? Did I forget to mention something? Does anything not make sense of what I've said? Because there is a lot of information to relay, a lot of things are intertwined, and so I might forget to mention something that's really obviously important, but I don't tell it. So did everything make sense about the whole chunk thingy that I introduced to you? So let's get rid of this one. Yes.
How do we determine if they are free or not? Are they sorted on free or are they sorted on some side freed and
No, only the freed chunks are in the list.
oh, okay.
Malloc chunks are not in the list. So the tcache, good question. The tcache, so let's say the tcache for the example. Tcache starts at the beginning with a null pointer. There's nothing in the tcache. And then, let's say we free a chunk, it will end up at the beginning of the tcache. So C1, and it will point to null, because null was there beforehand. And remember when we had on a slide the heap header, which is at the top of the heap, remember that? This C1 address gets written in the header. So that's how the heap knows, or the malloc knows which chunk is next in the free list, because the head or the first one is always stored in the heap header. And if we free another one, it goes like this. And that's it. It just keeps building. So this is the T cache, and but what then happens if malloc is called? Let's say all these chunks, so C1 equals C2 equals hex 21. So this is the size. What if we call malloc now? What happens? So these two chunks are free. And the point of tcache is that it is a cache. So here are two pointers, and then the program gets a call to malloc with a size hex 21. Will the malloc go and allocate new data, new memory, or it will just take one of the pointers here? What do you think?
Take one of the pointers.
Yes, so malloc will take one of the pointers. Which one? C2 or C1? C2, exactly. So the tcache is a LIFO list, last in, first out. It's like a stack. The last chunk that went into the list is the first one that will come out. Okay, cool. And here's some more data about it. So basically, I was talking, every chunk that is linked in a list like that has to be the same size. So in this scenario, both of them were hex 21. If we allocate two bigger chunks and then free them, they will be put in a separate list. Let's say that they are, I don't know, hex 30. Another list will start and it will collect the chunks of the size hex 30, and so on. All the way up to hex 408. I think that's 1 kilobyte or 2. I'm not sure, something like that. And every single tcache only has 7 slots. So you can have 7 slots in the tcache, and after that the tcache is full. You cannot put any more data in the tcache after the 7th chunk. But you have fast bin and unsorted bin, which are like layers of cache. So the first one is tcache. You can put chunks in the tcache whenever you free something. But if the tcache is already full, so it has already 7 chunks, the next list in the order is the fast bin. So the fast bin is exactly the same. It's a single linked list, just the name is different, and it holds 10 nodes instead of 7. That's the only difference. They are the same otherwise. And at the bottom, so the last layer of the cache is the unsorted bin. The unsorted bin actually takes in all the different sizes. Let's say that we are able to allocate 18 chunks and then free all of them, and they are all the same size, and they are all within these ranges. So hex 30, let's say. Then the tcache will get filled up, and also the fast bin will get filled up, and they will end up in the unsorted bin. But there is also an easier way to put a chunk into an unsorted bin. You just free a chunk that is larger than the tcache or the fast bin size. So in this case, it has to be larger than hex 408, and it will end up in the unsorted bin. The difference is that the unsorted bin is not a single linked list, it's a doubly linked list. So every entry points to the next entry in the list and also to the previous entry in the list. Why is that? Well, because there is something going on in the T-cache that is not happening in, something going on in the unsorted that is not happening in the T-cache nor in the fast bin. And that's coalescing. Coalescing is the thing I was talking before with the pref size. It's the merging of chunks together. So if you have two chunks that are on the heap, one right under the other, okay, and let's say that this one is hex 500 and this one is hex 700 in size. So they will be like this. Okay, let's say we have these two chunks. Now, if we free this one, what will happen? Here, we will write 500, 500, like that. Because this is the size of the previous chunk. And here, the size will change from 1 to 0. Because we unset the p bit. The p bit is the one that says previous chunk in use, p. And this one will go, let's say this is C1, C2. And this chunk will go into unsorted bin, C1. Okay, and you might be wondering what happens with the pointers because it's alone. Yeah, they get set to main arena. So the main arena is because we have no threads. We presume that we have no threads. This is the only arena that exists, the main arena. Why are the pointers set there? Because the start of the linked lists for the unsorted bin is in GOT of, or the BSS segment of the libc. It basically means that the libc has, it's also an ELF, so it has a BSS and the data and the text segments and so on. And the BSS segment is reserved, so at least 8 bytes of the BSS segment are reserved for the main arena. And also the head of the fast bin, list. The T-cache, as we said before, is located on the heap. It's in the heap header at the beginning. The unsorted bin and the fast bin are both located in libc. So this is where the pointers will start to point. Okay, but then we do step 2, and we also free this chunk. Now, what should happen is this. This should happen, C2, C1, and this should be the state of the unsorted bin after the second chunk was freed. And also here are the pointers. So this one does not point anymore to the arena. It points to this chunk over there. So this one will say C2. And here this pointer will say C1, and this will stay null. I'm not completely sure about this one, but I think it will stay null, but I'm not sure. Okay, this is what should happen. But because of the coalescing or merging chunks together, these two chunks will merge. How will that happen? With the use of pref size. So when we freed the C1, the pref size got written, and then when we free C2, the free function will check whether here is 1 or 0. If it's 1, it will say, okay, the previous chunk is still used, we cannot merge with it. But if here's 0, that means that the previous chunk is free. So potentially we could merge. And then we check this previous size. And if this size matches, so we go C1 pointer, C2 pointer minus 500, and if this leads us to here, C2 minus 500, then it will merge the two chunks together. There are some more checks, especially in the latest libcs, but the general idea is like that. The coalescing works in a way that first it checks the previous in use bit. If the previous in use bit is 0, it will check the pref size. If the pref size matches, so it doesn't land somewhere randomly on the heap, but it actually lands on a memory that looks like a chunk, it will say, all right, we should coalesce these two together, and the unsorted bin will look like this. Okay, and we have to also assume that down here are still some chunks. So it's not, top chunk is not here yet. So this is not top, this is not the top chunk. Because then they can also coalesce with the top chunk, which let's ignore that for now. And then we have this big chunk in the unsorted bin. So the T-cache is empty, the fast bin is empty. We only have unsorted bin that has one pointer in it. That is of size 500 plus 700. Okay. But what happens then if we try to allocate something? So the point of bins, the point of unsorted bin, fast bin, and the T-cache bin is to serve malloc. It's to say, okay, if any of those bins have some chunks in them, malloc will take them out from the bins and will put them to use. It will say, this is the chunk I allocated. And in this scenario, we don't have T-cache. T-cache is empty. We don't have fast bin. It's empty. But we have a pointer in the unsorted bin. So let's imagine that now malloc, I don't know, hex 300 is called. What do you think will happen? What would be logical thing to happen here? Exactly. So malloc will take a pointer from the unsorted bin, but it cannot take the whole thing because the whole thing is, how much is that? Hex B large. This is too big. So it will just say, all right, the new pointer is just C1 plus, I mean, the new pointer is C1 and the size is 300. This is what malloc will return. It will return this same pointer to the C1. Why? Because these two have coalesced together and they exist as one big chunk right now, and the pointer to this chunk is in the unsorted bin, this pointer here. And the malloc will just say, all right, I will return this pointer, but the size of the chunk will be as much as you requested. But it will be on the same memory as the previous two chunks. That's the point of caching and not allocating new memory. Did that make sense? It's difficult to explain, but did that make sense? Are there any questions? No? Okay. Good. So this is how malloc works. Yes, not in reality, but for our use case, good enough. What I want to say with this slide is that For example, we have t cache is and then we have fast bin. Here should be zeros. That's not correct. Like that. Okay, and then we have the sorted is null. Okay, so this is the scenario. Let's say you have this list. So what does this mean? Tcache has 2 chunks in it, and both are size hex 20. Then fastbin has also 2 chunks in it, but both of them are hex 30. This means that the Tcache for the hex 30 is full, because there's no other way that the chunks of 30 will end up in here. So Tcache, so this is the 20 Tcache, 30 Tcache is full. So that means it has 7 chunks in it. And the unsorted bin is empty. What will happen if now, so this is the hex 30. So what will happen now if malloc gets called? Let's say that we are calling malloc at 1, malloc 21 or 20. Based on what we talked about there and what says here, which pointer will the malloc return? So Tcache has 2 pointers, both are size 21. Fastbin has 2 of them, both size 30, and the hex 30 Tcache is full, and the unsorted bin is empty. Which pointer will malloc 20 return? Tcache, yes. So how does the malloc work? The malloc will say, all right, is the Tcache of size 20 empty? It will go look in the Tcache of size 20, and it will see, all right, Tcache of size 20 is not empty. I will take the pointer from there. If Tcache of size 20 were to be empty, it will say, all right, is the fast bin empty? Okay, if the fast bin is empty, are any of the large bins empty? In this scenario, we only have 1 large bin, it's the unsorted bin. Are any of the large bins empty? And the large bin is also empty, so the unsorted bin is empty. And only after that, it will say, all right, none of the caching has the right size of a chunk stored, so I will subtract from the top chunk. What is the top chunk? The top chunk is very simple. It just looks like this. It has prev. It's a normal chunk like every other, but here is a big number, let's say 22222F, something like that. And this is top chunk, and it's a very big chunk. Hex a lot. Could be around, it could be also a megabyte long, I think, something like that, maybe less. And after malloc sees that every single cache is empty, so the fast bin, the Tcache, and the unsorted are all empty, okay, it will turn to the top chunk and say, new chunk is top chunk minus the size. So in this scenario, it will just point it right here. And the size will decrease here. So it will become D. So X 2222D by 20. It will decrease, oh no, sorry, 0F. Sorry, 0F. So basically, minus hex 20 is what I'm trying to say. X this will tell the malloc that 20 bytes, hex 20 bytes, were taken off the top chunk, and they were reserved for the new chunk that we just allocated. And this one will be also pref size and 20. 1. Like that. Okay. Does that make sense? So we introduce the top chunk now. I know it's a lot of information. Heap is not easy to understand. It takes time. And now we also introduce the top chunk, which is another source of where malloc keeps pulling the addresses off. But yes. And we saw at the sketch at the beginning, the top chunk is always, always, always at the bottom of the heap. Always. So the heap, if you find the top chunk, heap is above that. Always. Because it all came from the top chunk. At the beginning, it's just the top chunk with a lot of space. And when you malloc, this space decreases for the chunks to form. That's it. Okay, what if we have this same scenario, but we say malloc 100, but in this case, unsorted has like that. So in this scenario, so this will return, what do you say? You say from tcache. Where will this return from? Unsorted. Yes, that's correct. And what will happen with this? Exactly. So it will return this pointer, this exact pointer, and the new pointer that will be inserted in the unsorted bin, or that will stay there, rather, is this one. And malloc will return that. Cool. Okay, and for the last case, what about now? So now I want to allocate a chunk of hex 800. Where will the chunk come from? What? Top chunk. Yes, exactly. Why? It's too large for all the caches. It's too large for the tcache, of course. There's no point in looking. It's too large for fast bin also. And in the unsorted bin, the largest chunk is hex 300, so we can't use that either. And so this will come from top chunk. Exactly. Okay. So the general idea is that whenever malloc is called, first the tcache and the fast bins are checked if the appropriate sizes are in there. After that, unsorted bin is checked, and also the other large bins, so the small and the large bin. And after that, top chunk is asked. But what happens if we say malloc this? These are Fs. So it's a very large allocation, larger than the top chunk. So it will go again through the tcache to the fast bin, through the unsorted bin. It will find no appropriate sizes in there. Then it will check the size of the top chunk. It will see that the size is too small for this allocation. But what then? Exactly. Process will go and call kernel for help and tell him that it needs more memory. Basically, it will allocate a new top chunk, and it will give it a big size, and put this. So this will come from mmap or kernel. And this chunk will be put on the heap with the m bit set. So here you have m, p, a. The m bit will be set because this chunk was m mapped, the big one. And this is it. This is the whole hierarchy of the heap. We will also take a look at it in the debugger, how it actually looks like, and it has a nice output, so you will be able to see the locations being done, the bins being filled up, and everything. Does this make sense? Believe me, if you are going to go and do your own research on this, you will find out that I've left out a lot of stuff, and that some of the stuff that we omitted is crucial, that something like that probably won't even happen. But the general idea is this. This should work in general. But if you find yourself in some specific cases, the malloc does behave differently. But in general, this should do it. Okay, now that we were able to go through the boring part of getting to know malloc, and yes, I know this is boring, now we'll take a look at the attack patterns. So when we were talking about stack-based exploitation, we said that every single technique, every single attack pattern must involve a stack-based buffer overflow. Otherwise, there isn't much to do on the stack. It's just, if you're able to overflow a buffer or something like that, then you can target the return address and you can redirect code. Cool. So to your surprise, there are also heap buffer overflows possible. This is when you allocate a chunk of size n and you write n plus something to it, it will overflow. So in this scenario, it would overflow. I just wipe this. If you were to write more than, let's say this one will be 50. This one will be, let's say 50. And this one will be 60. Let's say that you were to overflow from chunk C1 into chunk C2. When we did that on the stack, the idea was to overflow the return address, and when the function would return, it will return rather, it would return to our address that we chose. What about here? What can happen with an overflow? Let's say that you can overflow the body here, and you can write more data on the heap. What variables could you change? Size. So let's say, for instance, that this chunk is allocated, and this one is as well, and you found a buffer overflow that lets you overflow a chunk by 10 bytes. Then you will override the entire body, and you will be able to write in the size field. Is that good or bad? I'm sure you can't see it yet, but that is very bad. That is, from that stems most of the exploitation on heap. But why is that so different? We also had buffer overflows on the stack, and we said that in real-world applications, they don't cause us much harm because they are very easy to protect against. What about here? How would you protect against a heap overflow? Does anyone remember what was placed on the stack to make buffer overflows less or even not effective at all? Canary. Great. So on the stack, we had canary that was placed at the right under the buffer every time the function was called, and before returning, the canary was checked, and if it changed during the execution, that means that buffer overflow occurred. Abort the mission. Could we do the same thing here? And obviously not, because somebody would have done it already. What is the main problem? Why cannot we just put a canary here, the same as on the stack, and say canary, and then the buffer overflow happens? What is the problem with this? That is the problem, yes. But the bigger problem is efficiency. And when would you check for the canary? When it's in the stack-based exploitation, it's very easy. You check before returning, always. What about here? You can't check after every write. That would give us a lot of overhead. You can check when the chunk is freed, okay. But by then you could have already overwritten half the heap. So the main problem is that there's no easy way to protect against heap buffer overflows, because heap has to be fast and it has to be dynamic. You cannot have a static check in place that will say, oh, every time a free happens, let's check the canary. Yeah, by then you have already overwritten a lot of other chunks that will never be freed, but you still managed to overwritten them. So that's why heap overflows are a little bit harder to protect against. A special type of heap overflow is off by 1. Just from the name, what does that infer? Off by 1. Off by 1. Just 1 byte overflow. This usually happens when reading to a malloced chunk and you say while let's say I is less than or equal to some value, 500, and you have I going from 0 to 500. How many bytes are being written here? Let's say that you're writing here. Get char. How many bytes did you read? 1. Yeah, so how much? You increment I by 1 every time. Did you read 500 or 501?
0 is included.
Exactly. Actually, because 500 is included. Because it's an equal sign here. Because of less than. Yeah, so 0 all the way to... It should be 0, either 1 to 500 or 0 to 499. It shouldn't be 0 to 500. Because that means that somebody who's writing the code is probably wanting to write 500 bytes. But if he writes the code like this, it will read 501 byte. And this is an off by 1 vulnerability. It's also common because of negligence mostly. But the thing I like to say to people that are interested in heap is that with this 1 byte overflow and every protection enabled, you can still exploit the program with just 1 byte overflow. You have to be able to do it multiple times and also allocate and free multiple times. You can just have then people come to me and say, "Oh, here it's a malloc, and I've written 1 byte too much in the memory," and then return. You cannot exploit that. Yeah, or you're right. But if there is hundreds and hundreds of mallocs and hundreds of frees, which is common in modern day software, if that happens every time, that program is most likely can be exploited. So this is kind of the off by one vulnerability. We will take a look at the off by one vulnerabilities probably next time or the week after that, because in order to exploit off by one vulnerabilities, we have to cover overlapping chunks and coalescing in depth and stuff like that. But just as an interesting fact, it is possible. Okay, we already talked about this, why heap overflows are important. Okay, so the last chapter, the use after free. So as the name suggests, the use after free is a vulnerability where we are able to write or read from a chunk that was already freed. Let's say in this scenario that we free C1, and this happens, and the size, okay, size is already 0, and so on. So we freed, I'll say free, we freed C1, and then the logic of the application allows us to reuse this pointer that we freed to be able to write. Let's say we are able to write to the chunk again. As soon as we free it, of course, we get here the FD and the BK, because we freed the chunk. Okay, and this chunk, so the C1 in this scenario, I'll just wipe this. And the Tcache will look like this. What is the problem if you can write to this chunk? What is the problem if we can then write to there? What is this? Where is this address written? It's in the FD, the forward pointer. If we are able to overwrite the forward pointer, then this chunk, all of a sudden, points somewhere else. It doesn't point to null anymore, or to the next chunk. But the Tcache will still think that there's a chunk there, that there's something it can alloc or malloc. So in this scenario, we freed 2 chunks, and the Tcache changes accordingly. And then here's the special case of use after free is a double free. It's possible in some scenarios. It can happen easily, and the impact is just the same as the overwrite thing, but it's easier to manage it, because writing to a pointer that was freed happens less in code than freeing the same pointer twice. That can happen in loops and everything. So the scenario is we freed second chunk and the third chunk twice. And so the Tcache looks like this. What's the problem here? Just from what we learned today. What is the problem? Do you think that this is the intended behavior of the Tcache list? Okay, what would happen if we malloc here? let's say all are the same sizes, and we malloc the chunk 3 back. What would happen with the tcache list? So, as we said before, malloc will check tcache. There is a chunk present in tcache. So, it will return chunk 3 again. Like this. And now we have chunk 3 that is allocated, it's on the heap, but it's also in the tcache. So in a sense, it's free and allocated at the same time. And this happens commonly. Okay. What happens if we now write to chunk 3? Because we just allocated it, of course, we assume that we can write to an address we allocated. What will happen if we write to chunk 3? We write here in the body, but it's allocated, so it looks like this in the body. Exactly. We will be corrupting this pointer here if we were to write to chunk 3. Why? Because it's the same chunk, it's the same pointer. And so what we can do is we can overwrite the pointer, and this will happen. Now, we have just taken valid memory that we've allocated, chunk 3. It's valid memory. There's no use after free here. Okay, excluding the double free we just did, but by writing to it, we didn't exploit any vulnerability. It's a normal functionality of the application. But in this scenario, because the double free was allowed to happen, all of a sudden, what happened to the tcache? Our chunk 3 points to the invalid memory that we have written in it. Okay. And now we malloc again. Malloc goes into tcache. It sees there's a valid pointer in the tcache. The chunk 3 gets malloced again. And then this happens. Since we put a non-null value in the tcache linked list, malloc will think it's a pointer and it will return it. But in this case, this would crash. This would not happen, obviously, because 4A is not a valid address. But if we, instead of A's, put there some valid address, let's say on the stack or in the libc, we would be able to allocate a chunk that is not on the heap. It would be allocated on the stack, for instance. And if we are able to allocate a chunk on the stack, then we can overwrite the stack. We can overwrite the return addresses. We can skip the canary. We can return a chunk that points to the address right under the canary. We can bypass canaries. We can also attack hooks. We'll take a look at hooks momentarily. But the point is that we've tricked malloc to return an address of our choosing, an arbitrary address. In this case, for a proof of concept, we selected 441414141. How can we use that? So we can allocate a chunk wherever we want in the program. Where would you allocate a chunk? And you can also assume that you can write or read to the chunk. What happens if you allocate a chunk on the global offset table? and then you write to that address. You can override the printf address and redirect code execution on the next printf. The same thing goes if you allocate a chunk on the stack. You can overwrite return address. You can do rob chains, as we discussed before. You can also attack what is called hooks. So what are hooks? They are macros that are defined in libc and are used to append or replace free or malloc. For instance, if you write a value to free hook, the next time you will call free, the function that you've written on the free hook will be called instead with the same arguments. And we can use that. We can allocate a chunk on the free hook, overwrite what's there to, I don't know, system, and the next time we would call free, or the program would call free, it would actually be calling system with the same argument. And if we then allocate a chunk and write bin.sh to it and free it, we would basically be spawning a shell. That's the idea behind it. Okay. There was a lot of information and data here that we could probably use a few more weeks to cover all of that. Usually when I teach heap, all of what we've covered today would be done in 3 weeks. But the next time, if you show up, we will be taking a look at how we can leak libc from the heap. So today we focused on the overflows and the overrides, but we can't overwrite anything if we don't know where anything is. So we will be taking a look at how to leak libc from heap, how to use the heap overflow correctly. So what actually happens if we manage to overflow the sizes and how that contributes to exploitation. We'll take a look at fast bin poison. So today we're talking about tcache poison, where we inserted two of the same chunks in the tcache. And in the demo, I have the tcache overwrite, like we have a heap overflow and we can overflow into the tcache free chunk. We will get familiarized with house of something exploits. These are house of spirit, house of force, house of yada yada. There's a lot of house of something exploits that are targeted at malloc and free, and we'll take a look at them. Specifically house of spirit and house of force. And also next time I will show you where you can find for the next presentation in the references will be where you can find the different ways of exploiting heap. It's the guys over at Shellfish. It's a CTF team. They manage and also they manage a database of exploits, proof of concepts for different techniques of heap exploitation. I was thinking about putting it in the presentation, but I think I forgot. So I'll be definitely giving you guys that. Okay, well, that's it for now. The demos today are really short. I only have 2 examples, and they are not exploitation. They are just allocating and freeing stuff on the heap, so you get familiar with how all of this looks. So we should be done by 6. If we take a coffee break for 10 minutes now and return at 10:50 past 5, we should be done by 6. Okay. See you in 10 minutes. On the right, you can write. Yes. Can. No. Better? Okay. So zoom in a little here. Okay, so on the right hand side, we can see a simple C program that just allocates a bunch of chunks and then frees them right after. The idea is to take a look at how the heap is structured. You'll be able to see the top chunk, the header, and the chunks in between, and also to see what happens when the chunks are freed and the bins. So I've already ran the program in GDB, so compiled, ran the program in GDB, and I'm right now at the first malloc call. So the hex 14, which is 20, that's the first malloc call. So if we look at the mappings for the process, we can see that the heap would be colored light blue or gray, but we don't have any allocations or mappings of that color in the VM map. But right after I execute the malloc, if we look at the VM map, we can see that there was a new patch of memory mapped, and it's here it's labeled as heap. And now I can use the command this, which will show me the entire heap. Or I can also just say heap, I think. Yes. Great. So what is happening here? This and every chunk is colored differently. So this here is the top chunk, which is the purple color. Then the light blue is the chunk we just malloced, the size 21. We can see here is the size, here is the pref size, and this is the body. You can see that the pref size is set to 0 because the previous chunk is allocated. We can see that by the 1. And the size is set to 21. This entire thing here, so the yellow chunk, is the heap metadata. So here is allocated a chunk for the tcache lists. And whenever we will see when let's say, I think, yeah, this chunk right here will be freed, it will be put into a tcache list, and an entry and the pointer to that chunk will be stored somewhere here in the first segment of the heap. Okay, so right after that we will call free with an address 55626, and if we take a look at the heap, it's this address. So as I said before, the free does not take a pointer to the metadata, so the head of the chunk, but to the user data. And also malloc. Malloc does not return this pointer here to let you overwrite the header, but it returns this pointer down here that lets you write to the body of the chunk. And now, if I say free, and I'll just make this a little wider. Okay. If we just freed the chunk, we can see that the forwards pointer, so the FD, stayed the same. It's null. There was something written here, but that's because of my libc. So my libc is a bit newer, and some protections were implemented to not allow double freeing. We will take a look at what happens if we try to free this chunk again. But what I wanted to show you is this. So the pointer to the chunk we just freed, so the 56260, was written in the header. So now, next time a malloc is called for the size hex20, it will return this pointer. And if we were to free another chunk of size 20, this chunk here would start pointing to it. So the address would be written here. We'll see that momentarily. But now we will malloc some bigger chunks, which now doesn't seem like a very good idea because this heap will become larger and larger. But we just allocated the size of chunk of size 200, and we can see that this is the newly allocated purple chunk. If we then allocate chunk of size 2 kilobytes, so 2000, it's the green one. And we can see that our Tcache chunk is still there. So Tcache freed chunk is still on the heap, just it's not being used. It shouldn't be used. We still have the pointer stored, this A pointer. We still have that, but we shouldn't use it because the chunk is free now. Okay. Now we malloc another chunk of 2000, and I will malloc all the other chunks as well. Okay. So I've skipped to the point where every single one of these has been allocated. If we take a look at the heap, we can see the sizes 40, 40, and 30 are the 50, 50, and 40. And then we have two large chunks, both sizes 7E1 here. These are the 2 kilobyte chunks. And this is the D1 that is 200. Okay, but if you look at the code, we then go on to free a chunk at C, at pointer C, and then at pointer D. Do that. So we just executed the first free and look at the heap status. We see that here it says unsorted bin. And if we also type bins, we can see that Tcache has one entry. This is the first one we freed, the one at the top of the heap. And the unsorted bin got an entry as well. Why? Because we just freed a chunk of size 2000, which is obviously too large for the Tcache, it's too large for the fast bin, and so it was put into the unsorted bin. What will happen now is we will try to free a chunk at 56B30. If we look at that, should be 56B30. What I want you to take a closer look here at is the prev size. So before, when we freed the C chunk, so the chunk pointed at by the C pointer, it was put in the unsorted bin. And we can see here that two addresses were inserted in the backwards and forwards pointers. And because it's not a Tcache, it's in unsorted bin, it's a doubly linked list. So the two pointers, for now, are both pointing into main arena, for now. What will happen if we now free this chunk? It says also in the comments, but
they will merge.
exactly. So if we free the chunk on 56B30, it will coalesce backwards with this one. And what we are left with is one large blob of data, approximately 4 kilobytes in size. If we now execute that, we just executed the second free and look at the heap, we see that the chunk just got larger, and from 7, I think it was 7 something something, it became FC1. So basically the chunks merged together, and if we were to allocate a pointer or allocate something right now, and it was too large for the T cache, it would be taken from here. So this pointer would be pushed back, and by that, space for the newly allocated chunk would be created. What I want you to also see is this. What is this? I don't know if you can see, but there are some numbers there. Why? Yes, this is the remainder of the header of the chunk that we backwards merged, so coalesced. This is also what you must keep in mind, is that memory is never removed or never disappears. It stays as it is. And when we talk about chunks, it's important for you to understand that they are nothing more than pointers. In this scenario, just the pointer from here got moved all the way back to here. The memory stayed the same. So when we will be talking next time about leaks, we will see that here, for instance, is opportunity to leak an address because it's on the heap, and if we somehow were able to allocate a chunk there and just read it, we would get a libc leak. Okay. Now we will execute the 2 more frees. I'll just execute all of them. Okay. So I've executed the remaining 3 frees that were left. And if we look at the bins right now, we'll see that we have 3 Tcache bins that are partially full. So we have the hex 21, which has 1 pointer in it, hex 30, which has also 1 pointer in it, and hex 40, which has 2 pointers. Which ones exactly? So the 738, this is the 37, this one, and also the 340, so this one. And if we go at the top, on the top of the heap, we can see that we can find a pointer to 380. Why? Because this is as the beginning of the Tcache. So every Tcache linked list is, its head is written here. So the first chunk, the next one to be allocated, is written here. In this scenario, because we only have 2 of them, we in different size Tcaches, we can see they are both written here. So the 626 and the 310. When these 2, so if we allocate a chunk of a size hex 20 or 30, these 2 pointers will be released from the free bin and will be allocated again. And in the header, this will become null. But what is different is what happens if we allocate size hex 40 or here malloc 50. If we execute, so here is the call to malloc. If we execute it and look back at the heap and also look in the bins, we see that we've retrieved 1 chunk from the 40 sized bin, and also the address in the header changed. Before it was hex 380, now it's hex 340 at the end. And also the hex 380 chunk that we just allocated, if we look at the registers, we'll see that the malloc returned 57380. 57380 is our newly allocated chunk, and it still holds the address of the next chunk to be freed because it was part of a linked list. Okay? And does this make sense? Does this match with what we said on the board, with the drawings and all? So we have the forwards and the backwards pointer. When we free a chunk, the forwards pointer gets populated with a pointer to .next in the list, and so the linked list is generated, and the tcache is just a linked list. If we were to free 5 chunks of the same size, the list will just grow, and it will have just pointers to one another, to the third, to the fourth, and so on. Does this make sense? So I recommend you to play with this a little. Just allocate chunks of different sizes, free them, allocate them again, allocate a chunk with size, I don't know, 10 million, see what happens. Allocate a chunk with size 1 megabyte, see what happens. Maybe put some chunks in unsorted bin, try to allocate back from the unsorted bin, and you'll see how the pointer is slowly lowered to the point where it has no more space. But what I wanted to show next is the example of a tcache poison attack, and I've stolen this directly from the Shellfish how to heap repo. You can search for it. It's a first hit on Google. It's very useful. I've learned basically most of what I know from there, and we can, because it's the exploit technique here is quite known, we can just run it and we can read the output. We don't have to debug it because everything is nicely written in here. And what is the idea here? So it says the file demonstrates a simple tcache poisoning attack by tricking malloc into returning a pointer of an arbitrary location. So this is what we were doing on the board and also in the presentation. So we were doing tcache poisoning, where the plan was to trick malloc into returning an arbitrary pointer, and this is the same thing. Then it has some patches that prevent that. So how were they able to prevent a double freeze being used? Because chunks in tcache do not use their backwards pointer because it's singly linked list, they inserted a key in the backwards pointer, which is just an address to the beginning, so to the beginning of the tcache head, so the beginning of the tcache list. They just inserted the address there, and every time a chunk is freed, before it is freed, the free will check whether that key is already there. And if it's already there, it will abort, saying that the double free was detected. This is how they were able to circumvent the double freeze. But back to the exploit. So the idea is, the address we want malloc to return is this. This is a stack address. This looks like a stack address. It is a stack address of a variable they chose. And first, we allocate 2 chunks, both size hex 28, and their addresses are listed here. Then we free both of them, and by doing so, we place them in the same tcache in this exact order. So the second one is the first one that will be retrieved, and it points to the first one that was put into the bin. Then they overwrite the fd, so the first pointer of the chunk located here, so the first chunk, and they overwrite it with the address they want malloc to return them. So the pointer they want to trick malloc with, it's written in the fd. Then they allocate again, and what this does is it takes out the first chunk as it's intended, and it leaves in the tcache list just the address that we placed in there. Because we were able to overwrite a chunk that was already freed, we were able to put an arbitrary address in the linked list. And now the second malloc that happens returns a pointer to there. And the we got control is basically asserted at the end. We can also take a look at that in the GDB. So we'll break it main, run. We skip the virtual buffering, the puts. malloc. Okay, so now we've malloced the two chunks, the first and the second one, both the same sizes. Then we go on to free both of them. Now both of them are free, and we can see that the chunk that is being freed next is on 7.2f0. 7.2f0 is here, and the pointer to the next one in line is up here. And if we also take a look at bins, we see that tcache has 2 pointers inside. This is all normal. This is all what we expected. Then they proceed to do the overwrite. And if we take a look at the heap now, we'll see that what they have done is they have overwritten the linking pointer between the two chunks and set it somewhere else. So if we look at the bins now, it still thinks it has 2 chunks in the bin, but it only has 1 pointer, and the next one in line is not on the heap. That address is not from the heap. It's on the stack. But malloc does not really care. Malloc just checks if it's not null. If it's not null, it will allocate there. So now, when the first malloc is called, it will return. Oh, I've skipped one. I think I skipped one malloc. Yeah, I skipped one malloc. So what happened is we allocated twice, and the first chunk that was retrieved was this one down here, and right after that, the next chunk that was retrieved was the stack address, because we've overwritten the pointer to the next chunk in the list. And then there's just the assert that checks if we were successful, but just from this we can see, and also in the return register of the malloc call was the stack address, and we were able to overwrite the stack variable. Okay, so this is it from the demos. Are there any questions about the heap or what we've learned today? Okay, if you have any questions later, you can find me anywhere and ask away. But for now, that's it. Thanks for coming, and have a nice holidays. See you next week, probably. I will. You're all in the Discord channel, right? Okay, I will just post in Discord channel when the next workshop will be, and that's it. See you then. Thanks for coming.